Our presentation is about Code2Navigate, and we're going to show you a demonstration on how you can build your own navigation system. A navigation system you can use in your car or just on your phone, but in our case we're going to use it for planning bike routes. My name is Rob van Loon. I'll be doing most of the talking. This is my colleague Sander van Egmond. He'll be doing most of the coding for today. A little bit of background. My background lies in physics, and well, I always did quite a bit with data and visualizations and measurements. And at some point, I also got involved in working with data with a location in there. So I moved in the field of map making and geographical information systems. I liked it. I stayed around. I'm still here. Sander?
Yeah, I'm Sander. I have a background in environmental sciences. After that, I went following my interest in coding and programming, so I did an internship in that. And now I'm at a place where I can combine both by doing geo-IT at Ordina. Also, I'm a full-stack developer, and in my spare time, I like to make mobile apps.
As Sander said, we both work for Ordina. We're in the geo-IT unit. And a little bit about Ordina. It's like a company of 2,500, 3,000 people. And we work with our clients to come up with solutions based on 5 main propositions. That is intelligent, data-driven organizations, business platforms, digital acceleration, security and privacy, and as a developer, a very nice one, high-performance teams. If you want to know more about Ordina, we have a stand somewhere there in the main hall, or you can also write your contact details in the little papers that are scattered around the room. Back to our presentation. I told you my background lies in physics. So with this presentation, I'm very happy that I get to introduce one of the main concepts in physics, which is the principle of least action. And it's something that's used all over in physics in all kinds of fields. But don't worry, I'm not going to give a lecture on physics. What I'm going to tell you about is how to get from point A to point B. And if you apply the principle of least action, you will find that the optimal route, the shortest, the fastest way to connect those 2 points will be a straight line. It's not very surprising, no surprises there, but we can make it a little bit more interesting. So what would be the new route if there's a swamp in between? And you want to avoid the swamp, obvious. So one other route you could take is, it changes a little bit. You're going to minimize the distance you travel through the swamp, and you'll end up with a new route. But this might not be the best, the most optimal way, because, well, perhaps you can also go around the swamp, taking a different route altogether. So in this presentation, we're going to try to find the optimal route. Is that from A to B directly? Is that going to over this point C, or just around the swamp? And also ask some questions like, okay, well, if you want to avoid the swamp, how desperate are you to avoid the swamp? Do you want to avoid swamp at all costs, or is like 3 steps to the swamp okay? Or would be it okay if you the other distance you have to travel would be twice as long? Or, well, those kind of questions we're going to try and answer in this presentation. So in this presentation, we're going to implement a route-solving algorithm, trying to find the most optimal route. Going to tell you on not doing this on a simple network, but we're going to get some actual map data. We're going to combine some spatial awareness from other data sets, and we're going to do this with live coding. But let's start with the route-solving algorithm. We're going to start with a very simple network, 6 nodes, A, B, C, D, and F. And with all these nodes, we have a couple of connections between all the nodes. And with all these connections, there's a cost a cost you have to pay if you travel from one node to the other. So if you travel from A to B, the cost would be 1, but for B to C, that could be 3. Well, these costs could be either distances or it could be basically anything else. And for our presentation purpose, we're going to say we're going to start in point A, and our destination is going to be point E. And the algorithm, the way we're going to deal with this is, well, let's start with point A. The cost to get to point A is 0, because we're at point A. And from point A, we can either reach point B or point D. Both will take a cost of 1. So in our next step of the iteration of trying to solve this, this root solving, we're going to take, from this list on the left, we're going to pick one of those points, one of the nodes that we can reach, but we haven't visited yet. So in this case, it can be either point B or point D. So let's just take point B. Now from point B, we can either reach point C or point E. To reach point C, for instance, that'll take from B to C will be 3 points, but to get to point B, that would be already 1 point, so the total to get to point C would be 4 points. We can also reach point E now. E was our target, where we wanted to go to. It's going to cost you 7 points to get there. While we now can already reach our target, it's not necessarily the most efficient route, of the most optimal route to what we want to take. So let's continue. The next point, the next node that we're going to visit, again from the list on the left, we're considering all the nodes that we haven't visited yet, but we can reach. Going to take the cheapest one, and that's going to be the point D. From point D, we can now reach point F for 4 points, but we still don't know if we have reached our best route, so we just continue in the next step. Now considering point C. From point C, we can already, again, reach point E. Even slightly cheaper than we could have before, so this is a new best route, but we don't know yet if this is the most optimal route we're going to take. So let's continue, take one final step. We can still visit point F. So if we are in point F, we'll now learn that we can reach point E for yet even cheaper. And then there's still one last point that we haven't visited yet, so that's going to be point E. There are now no more other nodes that we can visit, neither should we, because we already reached our target now. Some of you might have recognized this algorithm that I just explained as Dijkstra's algorithm. It's a Dutch mathematician and computer scientist who came up with this algorithm, and it's basically used all over. So now we're going to implement this root-solving algorithm and trying to come up with our best route. Well, but before we do that, before we actually go and dive into the code, let me just quickly introduce you a helper class that we created. It's a class called Graph to build up the entire network, and has 3 main properties: edges, nodes, and costs. Nodes are the nodes, edges are the pieces we can walk over, and costs, well, how much it's going to cost to make actual that step. Let's start coding. Sander will be doing most of the code. We're doing this in Python because we both like Python, and well, we can, so let's do it. You see on the top of the file that we have this graph class that we are using, and on the bottom of the file you see, well, the same network that we've just introduced with the same edges and the same costs and all that thing. So we're going to write our root-solving algorithm. We're going to call that Dijkstra. So let's create a method called Dijkstra. It's going to take 3 input parameters. It's going to take something for the graph, the network that we're trying to solve. it's needing the starting point and our target. I just presented to you that we had this list on the left with all the nodes that we visited. So let's create a list of nodes that we're visiting. Already put the start in there. We're also going to keep track of all the known routes. So that's going to be a Python dictionary where we're just going to keep track of nodes that we can visit, the route that we're going to need to follow that to get there, and also the costs, how much it's going to cost to get there. Initializing it with 0 because that's our starting point. And then we can return just the known routes, so we can look up what the best route will be. So this is just the starting point of our method. And we're going to make a loop because we're going to step over all the nodes in our graph. We're going to keep on stepping to a next cheapest node just until we visited our target point, so that we can reach our target with the cheapest route. So we're going to do this in a loop, and in this loop we're going to keep on updating both the list of nodes that we visited, as well as the routes, the known routes that we can now to all the nodes. So we're going to do this in something like a calculate step, because we're stepping through all the nodes. Input parameter, well, of course, the graph. Our current node, so what's the node that we're at? And known routes going to be helpful. And the nodes we're visited. Going to initialize the current node because we're starting with our start point, so that's what Sander's going to do. Okay, so let's now focus on the method calculate step, where we're going to describe on all the steps required to calculate that step. And some typing for Sander. The first thing we're going to do, we can already say this is going to return both the visited and the known routes. Might be a good one. The first thing we're going to do is make a list of all the nodes that we can reach from this current node. Because those are the nodes that we're interested in and trying to, check how much it's going to cost to get there. Just getting the nodes of interest. Then we can loop over all these nodes. And one of the things then we want to do as a first go is calculate the cost to get to that particular node. The cost to that node is going to be the cost that's going to take to get to what's here called current node, and we're going to add the extra cost from the current node to the node that we're now looking into. So it's going to be a sum of those two. Seems right. And the second thing we're going to keep track of is the route on how to get there. So there's one tricky thing that we have to first copy the route to the current node. And then we can go and add the last step to our nodes that we're interested in. So that's the route to our current node, the route to our node that we're interested in is going to first be a copy, and then we're just going to append this last step. And now we know the routes, so we can update the known routes with this last thing. And then outside of the loop, we can already say, well, we now basically visited the current node, so we're going to also update our list of visited nodes. But first, update the known routes with both the route going to get to that node plus also how much it's going to be. And now add the current node to our visited nodes. This is almost correct, because one thing we haven't considered yet is what if we could already reach the node that we're now investigating. So what we're going to do is first check if this node is already in the known routes. If it is, we're going to check how much is it going to cost to that node with the route that we already know. So best cost so far will be the known routes and get the points or get the cost of the current node. And only if our cost to the node that we just calculated is less than, well, best so far, we're going to update that one. So I think we can just copy paste that, and if the our node is not in the known route, so we don't know yet how to reach it, then still this default applies. So basically, this is it to calculate, well, a next step on our graph. So I guess we can go back to our original Dijkstra function, since now we implemented the next step and we know how to get or update the visited and the known routes, which means we can now proceed in our loop, and we're going to decide which node are we now going to visit. So let's first make a list of all the possible nodes we can visit, and that's basically going to be the keys of the known routes. But we're going to take out all the nodes that we already visited. So nodes to visit is going to be the difference, basically, of all the possible nodes with the nodes that we can that we already visited. Then we're going to take the cheapest one. So that means that we have to go and look up the costs of all these nodes. So we're going to use a quick list comprehension for that, basically just a for loop to determine all the cost of the nodes. And now basically we're only interested in finding the minimum of this one. Unfortunately, you have to do that in a try-catch configuration, because nodes with cost can be an empty list, and then it raises an error, so we want to avoid that. So we're just going to put that in a try-catch, and using the minimal method to get the cheapest node. And if it does generate an error, well, you're going to just break out of the entire thing. This should be it. Are you ready to give it a try?
I think we forgot one thing.
We've got one thing, and then that one thing is we now made a list of we found the minimal value of the nodes with cost, and we're going to make sure that that's the next current node. Good catch, yeah. This should be it. Ready to give it a try? And of course, we're getting an error. Line 32, I hear. Let's see, 32. That should be a... Yes, that should be it. Although... That's better. Yes. Good call. We now can find the best route. It's going to cost 5, and it's going to over the nodes A, D, F, E, which is exactly that we saw earlier on in the example that we worked out. So we now have a route-solving algorithm in place, the Dijkstra algorithm. So far, live coding for now. But this is a very basic example. It only has 6 nodes, and well, it's almost faster to do this just by hand than going to write an entire route solving for this. But now we're going to add some real map data and making a real navigation system. So to load all this data, we've used data from OpenStreetMap. OpenStreetMap is an initiative that started, I believe, in 2004, where they got a big group of volunteers that went and started mapping their surroundings. So it's community-driven, with people who have local knowledge of what they're actually mapping. And if your group of volunteers is big enough, you can map the entire country. If your group is even bigger, you can map the entire world. So that's basically what the people at OpenStreetMap did. So that's how we're going to get our route data from. To prepare this data, we downloaded OpenStreetMap. The entire OpenStreetMap is a bit big, so we only selected the Netherlands. And even that is still relatively big, so we made a selection for our bike paths. First, we used a spatial selection, just in a part of the province of North-Holland. And then also a selection of all the routes or all the lines that are in there. Basically, we're interested in all the lines or the ways or the roads where you can cycle on. So that means we're going to skip all the lines that are marked with highway is a motorway, because you cannot cycle on a motorway. Also, we're going to skip all the lines that are marked with highway is a footway, because you don't want to cycle on a footpath. And, well, there are also a little bit of other tags where, for instance, some lines are tagged with bicycle is no. I think that's pretty straightforward. We made a selection of this and then started to node the network. With noding the network, what I mean with that is, well, here's a small selection of it. The background is OpenStreetMap, and all the black lines, that's the lines that we selected before. Well, if you now zoom in on, say, this part, you will see that basically looks like this. It's a T-shaped figure where, well, the lines are not connected. So with noding the network, I mean that we first gonna cut the top line, the horizontal line, and make a cut, and then glue all the lines together and make a real node of there. And this is just one example, but we did that for the entire data set. But with preparing this node, we also then made the rest of the graph by numbering all the nodes and of every edge updating which edge connects which node to which other node. So that is how we created our network. So with OpenStreetMap, the idea is that you get an accurate and an up-to-date data set. So let's use this for our bike application. What we also prepared, because we could, is a simple Django web application where the two main files are going to be the Dijkstra file that we actually just created and implemented, and a HTML template file. Then with all the Django goodies that you get with creating a web application, if you visit the web page, you're going to get some HTML, CSS, and a bit of JavaScript. We use a JavaScript library called OpenLayers to be able to show an interactive map on the screen. In first instance, that's just going to be a background map with an overlay of all the bike routes that you can take. But then in this application, you can just click and select 2 points that you want to visit, and basically your start point and your end point. The application will then send a GET request to the underlying web application. You get a JSON back, and this JSON we can then draw onto the map. As a first go, we're going to build look for a nice bike path going from the train station in Hilversum to the Muiderslot. So here's the web application we built. You can, Sander is now reloading it. So we just made a small selection of, on the bottom right, that's the city of Hilversum. The train station is about there, somewhere. And we're going to cycle to the Muiderslot, which is about there somewhere. And we're going to use the shortest path. I happen to live actually in Hilversum, so I actually cycled once to Muiderslot. It's a very nice route, especially when the weather is nice. And our algorithm that we just implemented is now going to calculate the route. And here in the thick red line is what it came up with. It's a short distance between, well, the train station to Muiderslot. Since I live in the area, I know a bit how to get there. This is not the route I want to take. If I'm going for a nice bike ride, going to cycle, going to enjoy myself, I don't really want to go and cycle first through all the way through Hilversum, cycle through Bussum, and then later on cycle along a highway. If you're going for a nice bike route, this is not really what you're after. So the question is, can we do better? Can we find a bit more interesting route? Perhaps we can. So what we're going to do is use some spatial cleverness. Because with GeoIT, we don't just provide data or do some simple data analysis. We also are going to combine data, trying to come up with better solutions. So what we're going to do is use a different data set. So we downloaded a data set from as open data from the Dutch government with land usage. So here you see a small section of it. The red is like builded area, so houses and stuff. Green is either forest or agriculture. Blue is water. And we're going to we have this image, and we're going to plot on top of it our bike routes. These are these black lines. And with some geo-analysis, we can, well, first select all the areas of the city areas, and then do a spatial overlap, trying to find all the bike routes that overlap with the built areas. After that, you can say, well, we don't want to cycle through built areas. We prefer open spaces. So with this selection, we can then say add an extra penalty to all these routes that are now selected, saying I want to avoid all these routes, and I'm going to say that I'm happy to cycle twice as long somewhere else if I can avoid this. So basically, we're just going to multiply all the distances by 2. If it's a nice, warm, and hot day, you might actually want to say, well, I prefer cycling along the water, get a bit of a cool breeze. So we selected all the water in this picture, made a small buffer so you can select all the bike lanes that are close to the water, and then you basically come up with this selection. With this selection, we did multiply the distance to get some extra cost, but actually with a value less than 1, so we're making it more attractive to cycle over this over these cycle paths, so we get to cycle along the water. And we can show you that we have 2 extra buttons. One is to avoid buildings, and if we're running that, you'll see that the route we're going to take is slightly different. We're going to avoid Bussum altogether and cycle a bit longer through nature. And that is going to be that route. Cycling more through nature. Which already is much better than the one through the red one to the city. If you would say, well, I would rather cycle more along water because it's a hot day, then, well, in a moment it'll show you the blue route. These processes take a bit longer to calculate because in our example that we started with was only 6 nodes. The network we're analyzing now is more like 16,000 nodes, so it takes a bit longer. But here you go, this is a new route, cycling along the water, much nicer than cycling through the city. Well, you can also see that Sander is moving the map up and down a bit. You can select completely different nodes to make a new calculation. You can fire them up all 3 in one go to see the differences in, well, whatever route you want to take. Well, this is actually 3 times the same route, but you can see that you can play around with this. And actually, yesterday we had some time left over, and we really found, well, we're planning our next trip, basically. As you can see, this is all interactive, based on the JavaScript libraries, and then sending the requests to the route-solving algorithm that we just implemented. It's well, nice to play around with. You can see you get all kinds of different roads. So basically, that'll now bring us to the end of our presentation. I hope you enjoyed the route, and are able now to well, to basically build your own route-solving algorithm, extract some data, for instance, from OpenStreetMap or any other data source. You can overlap other data sets. Perhaps you want to add some interesting points of interest to find out what is a good spot to have an ice cream on the way, or perhaps a beer in a pub. Or you might even think of different things to add. For instance, add some weather information, finding out at which part of the route you will have, you're facing the wind, and on which part you're riding with the wind, optimizing your route in that way. Or weather information to avoid showers. That's also a very nice one. So if you have some good ideas, or are interested in finding out what you more can do with geo and geographical information systems, please come by. We're down in the main hall, or fill in this contact form. Thank you all for your attention.